If you somehow stood on the surface of a neutron star, you would not slowly collapse. You would not even feel pain. You would be crushed into a layer of atoms less than 1 millimeter thick before your brain could register what happened. Most people think neutron stars are just dense. They are. But dense does not describe this. A neutron star is what happens when a massive star collapses so violently that matter itself is forced past its normal limits. When a star explodes in a supernova, its outer layers are thrown into space, but the core falls inward. Electrons are driven into protons. Protons become neutrons. The empty space inside atoms disappears. What remains is a sphere about 20 kilometers across, smaller than a city, but heavier than the sun. All the light, all the fusion, all the hydrogen is gone. What remains is gravity and crushed matter balanced against quantum pressure. On the surface, gravity is roughly 200 billion times stronger than Earth's. That number sounds abstract until you imagine dropping something from 1 meter above the ground. It would not fall. It would strike at over 7 million kilometers per hour. Anything soft would flatten instantly. Your body would spread across the surface like paint, compressed into a sheet thinner than a fingernail. The crust itself is iron, but not iron as we know it. The atoms are forced into a crystal lattice, under pressure so extreme that mountains cannot exist. The tallest structures would only be millimeters high before gravity crushes them flat. The surface is smooth, rigid, and unforgiving. Beneath that crust, nuclei begin to deform. The pressure squeezes them out of spherical shape into rods, sheets, and tangled structures. Physicists call nuclear pasta. The name sounds harmless, but this material may be the strongest known in the universe, billions of times stronger than steel. It is matter reorganized under crushing force, stretched and flattened into shapes that cannot exist anywhere else. Go deeper, and neutrons begin to leak from nuclei. They are forced out by pressure and start flowing between the remaining structures. Matter becomes both solid and liquid at the same time. The temperature may reach 1,000,000 degrees, but heat is irrelevant here. Gravity dominates everything. Beneath this layer lies the outer core, a region of pure neutron fluid. Not a normal liquid, but a superfluid. It flows with zero friction. If disturbed, it would spin forever. Inside this fluid form, perfectly straight vortex lines aligned with the star's rotation. Some neutron stars spin hundreds of times per second. The entire interior adjusts to that motion through quantized vortices that never bend or merge. A single teaspoon of this material would weigh millions of tons. Protons in this region form a superconductor, allowing electric currents to flow without resistance. These currents generate magnetic fields trillions of times stronger than Earth's. Strong enough to distort atoms. Strong enough to strip electrons from matter at close range. So far, this physics is extreme but understood. We can create superfluids and superconductors in laboratories. But deeper still, our certainty begins to weaken. At the inner core boundary, density reaches the same density found inside atomic nuclei. Imagine compressing all of humanity into a grain of sand. That is nuclear density. At this point, neutrons themselves may not survive intact. The pressure may be sufficient to break them apart into quarks. If that happens, the core becomes quark matter, a dense fluid of fundamental particles normally confined inside protons and neutrons. Other models suggest hyperons could form, particles containing strange quarks that barely exist under normal conditions. Some theories predict strange matter, a state where quarks bind in ways that could be more stable than ordinary matter. Or perhaps something entirely unknown, because no laboratory on Earth can recreate these sustained pressures. At the very center, general relativity and quantum mechanics disagree. One predicts one behavior, the other predicts something else. We cannot test which is correct. Some models allow for a microscopic black hole at the center, not large enough to consume the star, just a tiny region of collapsed spacetime. Others say pressure would prevent that from forming. The truth is, we do not know. What we do know is there is a limit. A neutron star can only support about 2 to 3 times the mass of the Sun. Add slightly more mass, and neutron degeneracy pressure fails. In milliseconds, the star collapses into a black hole. The transition is abrupt. One moment, a neutron star. The next, an event horizon. The difference between them can be a small amount of added matter. A fine balance between collapse and resistance. So what is inside a neutron star is not a simple answer. It is layers of crushed iron, nuclear pasta stronger than anything we can build, neutron superfluids spinning without friction, superconducting currents generating impossible magnetic fields, and possibly quark matter, or exotic particles that challenge our understanding of physics. It is matter pushed so far that the distinction between particles and fields begins to blur. It is a natural experiment at pressures and densities nothing else in the universe sustains, except perhaps the moments after the Big Bang. And all of this exists inside a sphere small enough to drive across in minutes. From the outside, a neutron star looks like a small, dim object. But inside, it is a vertical descent from normal atomic structure to the edge of theoretical physics, from iron to pasta to superfluid to quark soup. From equations we trust to equations that hesitate. It is not just a dense star. It is a boundary between what we understand and what we do not. And the fact that we can measure their pulses, detect their gravitational waves, and infer their internal structure from light years away does not make them less mysterious. It only sharpens the question. What is really inside a neutron star is not just extreme matter. It is the point where gravity almost wins, where quantum mechanics pushes back, and where our best theories strain under the weight of reality. That is what sits inside that 20-kilometer sphere. Not just neutrons, but the limit of physics itself.